In earlier videos, we fitted XAFS data with Feff calculations for arsenic sulfide and for iron oxide. In this video, we'll do one more example with a metal oxide because you can't get enough practice at looking at all of the steps and the full XAFS analysis. And we might learn some new things along the way. Hi, I'm Matt Newville, and this is part of the video series for using Larch for XAFS analysis. In this video, we'll use data that is quick XAFS data on palladium oxide. It's actually pretty similar to iron oxide, but gives it enough of a variation that I think it's instructive to look at some of the subtle features for XAFS analysis. So we'll start with opening the data file. Actually, this data file in the palladium oxide folder, this should be in the data stream that you can get at for the course or available in the video, in the links below. This data was collected at Spring 8 in a manner in which they collect the angle, but not the energy of in the x-axis. So I'm going to want to rearrange this data. So this comes back all the way to the beginning of reading in XAFS data. The data columns here were parsed oddly. So I'm going to re-edit the names of the files. I'm going to say edit array names. I know from some experience with this data set that this is the first column is the drive value for the angle, and then it's the read angle read. The third column is a constant, and that must be just the collection time. I'll call it collect time. And then the last two columns are I0 and I1. So I'll select this. So this would be reading in arrays of data from angle. So here we'll select read angle. That's probably more accurate than drive angle. And then we'll tell it that it's not raw data, but XAFS data. Of course, to convert angle to energy, we need to know the lattice constant. So we'll tell it that the units are degrees. If we go back to the text file, it actually has subtly the lattice constant used for the silicon 311 micrometer there, right there in the data file. So this is what they intended you to use, so you can just put in that number of 1.63 angstroms. And now, if we go back to plotting the columns, we can look at I1 over I0, and then take the natural log of that, minus natural log of that. So that looks like our palladium oxide spectra with a K-edge of around 24,300 eV. So I'll say okay, but we're not done importing this data yet, because a box is going to come up that says, warning, this data set may need to be rebinned. With a lot of quick XAFS beam lines, they'll collect very many data on very finely gridded energies arrays, and we want to convert that to our normal XAFS range. That's partly to be able to do a better signal averaging and data collection of the noise. So here a dialog comes up to rebin the data into sort of a normal XAFS grid where there's a pre-edge range. We'll sample that at, I don't know, let's make that 2 volts. It's fine enough. And for the most part, these values don't matter, but we want to select the Zane's range. We'll put that on a grid of 0.25 eV. And in the XAFS range out to 17.8 keV, we'll sample that at 0.05 inverse angstrom so that the data is evenly spread in K for extended XAFS. And I'm just going to say save overwrite here, and that will then save the data, and then we're done. That will then save this data in what I would call a reasonable reasonable sampling of energy and over the full range. So we can unzoom this all the way. The normalization looks fine. We can look at what the normalization did from the raw data. That seems reasonable to me. I don't think we need to worry too much about getting the normalization more perfect than that. It goes from about 0 to 1, and if we want to worry too much about the coordination number at the 10% level, we would want to do more spectral analysis on different spectra anyway. So here we'll just go to the XAFS window and look at the chi-of-k data. And this is already a very interesting spectra, and this is sort of why I wanted to show it to you, that there's a lot of things going on in the spectrum. So, and with the window function, just to like get an idea, would be sort of the window function that we might use for this spectrum. We can use something more, less broad. But this is okay. This is to 17 inverse angstroms. So we'll try to fit this spectra. So this is palladium oxide, and so we'll go do a Feff calculation for palladium oxide. So we'll go to our browse CIF structures and run Feff window. And I don't know what the name of the palladium oxide mineral might be, and I'm not sure it's going to be listed here. But let's say search for CIFs that include palladium on oxygen. That'll be a small number already, and one at the top, palladium oxide, palladiumite here, looks like a reasonable candidate. It's got a space group. All right, so then it's got like 2 atoms in the unit cell. So let's try this. From examples of this, I believe this is correct. There's our input file. Palladium is the absorber. There's a palladium neighbor, and there's oxygen neighbors, 4 oxygen neighbors at 2 angstroms, and palladium at 2 slightly different distances. So that's interesting. And we'll say 6 angstroms is plenty for the first couple of shells, and we'll just run Feff on this example. And again, there are other choices. So here it gives a nice description. There's palladium oxygen, 4 equivalent paths at 2 angstroms, and 4 short palladium bonds, and then 8 longer palladium bonds. Okay, that's all fine. Let's close this. And so if we thought about that, let's go back to our XAFS tab and plot not just the chi-of-k, but our Fourier transform. So here's our Fourier transform out to 10 angstroms. You can see there's a peak that must be the palladium oxygen, and then this split peak here that's probably partially the 2 palladium distances that are pretty close to each other. So that seems reasonable. And then there's higher frequency shells, higher R shells, that we'll just skip for this in the interest of time, or maybe we'll come back to them in a bit. So let's go to the Feff Fitting tab, and we're going to do our fit in R space with a k weight of 2 with these Fourier transform parameters. We'll fit the data only out to, say, something like that distance, 3.8. I'll round that up to 4. Why not? That's fine. And now we want to read in our Feff files for those. So we'll go to the Feff menu and then browse Feff calculations. I had cleared these out. That's a fine thing to do. I cleared them out, and we now have only this one calculation. I want the metal oxide at 2 angstrom, and then I'll take both of these. They look like they're so close that they overlap. And then there's a triangular path, palladium, oxygen, at 3.5 angstroms, but it's got a very low importance factor, meaning that it has a very low intensity. And then there's a palladium oxygen at 3.6, so we might want to include, but for now we'll stick with these 3 paths and just look at these. So we'll import these. Again, these come in, and we fill in expressions for amplitude and E0, delta R, sigma squared. Those are our typical XAFS parameters. And when we do that, there's a separate set for delta R and sigma squared for each path. But E0 and S0 squared are taken to be the same, and the amplitude of the path is the expected, the degeneracy, or the starting degeneracy for that path times S0 squared. That's often a good approach to start with when using a crystal structure to analyze spectra, but you can definitely alter those parameters. And then we get a parameters page that has all of those, the starting values for all of those all of those path parameters that we're going to use in our expressions. So if I plot the data with the current model, I get this. So there's the oxygen. I could say plot each path individually. There's the total model in red, which is actually a little undercounted. We probably have our Debye factors a little too high. These are often reasonable values, but for low temperature data, which I think this might be, it's often these will often refine to smaller sigma squared values. So we have an oxygen path and two palladium paths that aren't exactly on top of each other. And that's our chi of k data, and we can look at that in k-space. And that's kind of a mess, but let's put an offset for those paths there. And those are then the total in red dashed, and then the oxygen contribution showing peaking up at low k, as you would expect for oxygen paths, as we discussed in the paths, and I'll show again. And then these two paths from palladium on top of each other. And we can, so that's what those are. We'll come back to that in a second. And we can run a fit. Actually, before we run a fit, let's go look at that in more detail. Let me just change the offset back to 0 and look at, I'm going to hide the data and hide the model and hide the oxygen and look at those two palladium paths. So those two paths for palladium are interestingly different. They're close in distance, but not exact, and so they have a slightly different phase. And you can see that if you add those up, they're going to be out of phase here and in phase here. And so those will give an interesting pattern. In addition, each of these paths, each one of them sort of has an envelope function that looks like it's not simple, but has this beat here at around 5 angstroms. And these are separate effects. So let me go back to this page here and plot f of k. I'll start with the oxygen and plot f of k, because we saw this before. F of k for oxygen peaks at around 3 or 4 angstroms and dies out. It's got an amplitude of about 0.7, and it dies to below 0.1 above 10 or 12 inverse angstroms. For palladium, on the next row, on the fourth row, we see an f of k that looks like this. That also peaks at about 3 angstroms, but has a big dip. Actually, the phase also takes a big change. You can see here, this is the phase going from about 0, some number close to 0, to some number close to minus 20 at minus 20, so that the slope is minus 1. But it also has a big change here. Actually, this change in phase is about pi over 2. So it's like there's a big phase shift at this dip, and then the amplitude continues out to stay very high, much higher than oxygen, out to k of 20. So now if I plot those paths again, and the same one for the palladium 342 path is going to look very similar. The amplitude that's all electron scattering, the scattering of the palladium, the photoelectron leaving the palladium and scattering from palladium. So if I now plot those paths again in K, you can see that beat. It's peaks up about 3, it has a dip about 5 to 6, and then it starts up again. So that is just the amplitude function wrapping those oscillations. Each of them have it. And then in addition, because they are different distances, they will go in and out of phase and so have a beat to them. So the palladium scattering in this spectrum is pretty complicated. The oxygen seems much less complicated in contrast. Okay, so now we can just do a fit. We can say fit the data to this model, and here's our fit and our parameters page with the values. So we got values for E0 and S0 squared is about 0.8. Typical. The distances don't refine very far at all. So this is probably pure palladium oxide. The people who made this sample did a much better job. than some of our earlier samples. And we can also see that there are sigma squareds that are actually pretty low, 0.002, 0.004, 0.05, and then our mess of a spectra. So I'll hide the individual paths, and there's the best fit model in red dashed with our data in blue. And you can see that if I just plot the oxygen path for that model, it's right there. It's kind of bothering me. So one of the things that you can do with this is you can always change the colors and the line sizes and so on. So I want to make those a little bit bolder. Okay, that might be better to see. Except for those who are red-green colorblind, I'm looking to show the second and third are always red and green. The total model there shows the palladium and oxygen contributions, and the individual palladium contributions or oxygen contributions there are shown. So that is the model. It's very complex because of this beating that happens both here and here at 6 inverse angstroms, and here around 12.5 inverse angstroms from these two palladium paths beating against each other. They're completely out of phase here at 12.5 inverse angstroms. Okay, so that's all the photoelectron scattering parts of that. But here we notice that if you notice, we can look at these parameters. I'll bring up the path parameter page to look at the results. We have fitted variables, and we also have the path parameters there's the values for oxygen, E0, the R, the refined R values. And you'll notice here that the two sigma squareds for oxygen, or for the palladium-palladium scattering, the two sigma squareds for the palladium-palladium are pretty similar. Actually, the delta R's are pretty similar too. They're 0.014 and 0.017. See, one question you might ask, and this is common for analyzing XAFS data, is can we get a slightly better improvement by combining, refining, or modifying the variables that we fit? For example, in this fit, we set each of the sigma squareds and each of the delta R's for the two palladium paths to be different, completely different variables, free to vary from each other. But we didn't do that for E0 or for S0 squared. We set those to be the same for all paths. There's some physical justification for that. E0 should be the same for all paths, at least from the same Feff calculation. And S0 squared is meant to be a parameter that is a physical parameter that applies to all of the spectra. But from a fitting point of view, you might ask, well, if these two values for sigma squared are so close, maybe we should just make those one value and thereby reduce the number of variables in our fit. How different are those, and could we get a better statistics and better fit if we tie those parameters together? For such good data here, where we have such good fits and such high quality data going out to high K, that's not so necessary. This reports that we have 28 approximately independent parameters, and we're using only 8 to fit this data. But we might for data that's less good or goes out less far in K, the number of independent points will be reduced. And as we're trying to fit more variables, this kind of question will become more important. So let's just try that. Let's look at how you would do that for this kind of spectra. So we have these path parameter expressions here for palladium at 3.42 and palladium at 3.03. If I go back to my parameters page, these were all varying independently, and I can constrain them to have the same value. So I could say constrain this parameter to be sigma 2 PD303. Now this will vary in the fit, but it will always take the same value as this variable took. So let me do that, and let me also do the same for the delta R, because those were also very close. And it might be that we really only need 6 parameters instead of 8 parameters. And again, for this data set, it looks pretty good, but let's try that. So we have now these two parameters for the palladium 342 path to be constrained to be the same, take the same parameter values as the fitting variables for the 3.03 angstrom palladium path. Okay, so I'm just going to hit fit for that model. And we get, now the most recent fit is at the top. So this is the new fit with 6 variables. Number of independent points is the same. Chi-squared got worse, and reduced chi-squared got a factor of 2 worse. So it's worse to add those two parameters, to have those two parameters be tied together, which is interesting. We could try one at a time. Now we have, we could try one at a time. So what if we just, I could change delta R to a variable. Let's try that, fit that model. And that is also, that's no improvement at all. Now we have 7 independent variables. That the fit is a little bit better, but the reduced chi-square compared to the fit we did with the first fit with all 8 parameters varying is still significantly worse. So let me flip that. Let's force the delta R's to be the same and allow the sigma squareds to vary independently, but the delta R's be constrained, and try that fit. And that's better than our previous ones, but comparing fit number 1, our most recent fit, with allowing sigma squareds to be independent but delta R's to be the same, compared to the one where they all floated independently, it's still a little bit worse in terms of as a measure from reduced chi-square. And then also these 2 information criteria, Akeki and Bayesian, these should be lower. And they both, all 3 of these numbers are different attempts to be statistics that you can compare even when the number of variables changes between the different fits. They all are better. All 3 of them are better for our first fit that we did, number 4 here, compared to the most recent fit. So that suggests to me that varying delta R independently for all of these paths is significantly improving the fit. So that would be the main point I wanted to take away from this data set, is that how to do that sort of analysis of what's important to fit and what's not important. There's one more thing I want to try. So the right thing to do would be to vary all of these. But there's one more thing I want to do with this data set. This is probably low temperature data. I don't know for sure. But one of the questions that often comes up for XAFS analysis, and you will see this often, you will hear this often, is delta R for this data set is slightly negative compared to, actually it's almost within the noise level. It's 5 times 10 to the minus 3 plus or minus 4 times 10 to the minus 3, or maybe 6 and 5. It's very, very close to no refinement of the crystal structure distance, but it's a little bit negative. And one of the questions that often comes up for measuring especially the near neighbor oxygen distances is, did you try a third cumulant? So all of the analysis we've done so far with having an R value and a sigma squared assumes that the distribution of atoms for a path is Gaussian. That is, there's an R value that's a centroid to a Gaussian, and then sigma squared sets the variance, or the, of the variance of that distribution of distances. So it's R 2.01 plus or minus the square root of 0.02 would be the range of distances. So if we use a third cumulant, that adds a skew parameter to that distribution, allowing it to be asymmetric. And the asymmetry can actually be to favor the closer bond distance or the further bond distance. Both of them are plausible effects. So let's go try that. We have our 8 parameters. Let's add a 9th. And all we have to do for that is to go to our oxygen page and type in a parameter name. I'll just call it third for 202, and I'll just to keep that nomenclature of using the variable name with the path consistent. That seems like a decent rule of thumb to try to use. It's sort of easier to figure out what the things mean. Now, when I did that, it already added a parameter with that name and set it to be variable. So that's fine. We can just hit. So now that's going to be varied. It's going to start with a value 0.01. You know, we could start with that as you know, some other value if we wanted. We could also change the starting values for the other parameters. This has worked pretty well. Like, let's see, S0 squared was more like 0.9. E0 was more like 0.05, which is pretty good, actually. And then, well, we'll just let all those go. Those were all fine values. So the sigma squareds all went a little lower than they started at, but not such a big deal. So we'll start with, we can change the starting values, and we'll add this, now we'll add this third cumulant. So again, I'll just hit fit. And at looking at the fit, we don't see really any like real change. So I can select this fit. The first one we did, that's that fit. That's the first one. And I can select this one. Show that one. That one's fine. But now we can compare the values for these parameters when we included the third cumulant. So first of all, we could look at the variable. The third cumulant we find to be 3 times 10 to the minus 4 plus or minus 1 times 10 to the minus 4. So that means that it's not quite consistent with 0. It's a small number, but it's also well constrained. It's minus 3 plus or minus 1 times 10 to the minus 4. In addition, you can see that the chi-square, even though we added a variable, we now have 9 variables in our fit, reduced chi-square actually went down, not quite significantly, but a fair amount. And both the Akeki and the Bayesian information criteria also each went down a bit, from minus 16 to minus 21 and from minus 5 to minus 9. So all of those are slightly better. So this is a better fit. So that's probably the best fit for this data set. Again, we can look at the path parameter. The full information on the path parameter page is a plain write out of text. The third cumulant again is 3 plus or minus 1 times 10 to the minus 4. That gets multiplied by k cubed, so it's a large enough value to actually impact the spectrum. There are high correlations between parameters. Delta R and E0 will typically be correlated, and the sigma squareds and S0 squared will also typically be correlated. So that's then shows how to test a third cumulant. You'll often see that the opposite case, that you try to add a third cumulant and you get a value that's small, but its error bar is enormous compared to its value itself, so that it's consistent with 0, and that the reduced chi-square and other information criteria don't improve by adding that variable. Here, this is the case where it does improve the fit to include the third cumulant. So that's often a good thing to test. It's simple to do. So you're almost remiss if you don't try it. And hopefully someone will catch you at that, and we'll say, you should really try the third cumulant and see if that might help change the values for your fit. I should say also that when we do this, the value for E0 or for delta R, let's look at that. The value for delta R for the oxygen path went from 2 when we used the third cumulant, and it was larger than that, wasn't it? It was 201. So it dropped by a hundredth of an angstrom when the third cumulant was included. So here was delta R was minus 0.005, and with the third cumulant competes with that, but now it's from 0.05 to minus 1 angstrom, so it's a full picometer refinement, lower in distance. And that's not reporting the third cumulant there. We're looking at the wrong one. There, show that there. Yes, now that's showing the 30 cumulant and delta R is minus 0.2 angstroms, 0.02 angstroms, 2.5 even. So I think that's a better fit, and it also shows you a few things. First of all, the way two paths that are close together in distance can beat against each other, and how the third cumulant can be important. I guess one final thing to look at for this data set is what we didn't fit. And again, here's the, even with all of our parameters going, there's still this stuff at very high frequency that we didn't fit here in this spectrum. And that's clearly, when we look at that in our space, these strong paths that continue out. And that's because palladium is a high Z atom that's going to scatter well, even when it's at 4 and 5 angstroms. And we have these tight paths in this very, very well ordered crystalline system. So I hope that's helpful, and I will move on to another example in the next video. And I hope that if you have any questions, leave comments or suggestions in the comment section below. And I hope this helps you with fitting XAFS data. Thanks.